Hi, we're going to be going over problem 6.2. And this is specifically going to cover shear flow. Now, there's a difference between shear flow and shear stress, one being the how much stress is flowing through a connection. That's shear flow. And then shear stress is how much stress the material feels at that specific location, which would be a different problem. So, in this problem, what we have is an I-beam. And they call it an I-beam because it looks like an I-shaped beam. Pretty cool, huh? And so dimensionally, I think I'm going to be kind of off, but whatever's. I'll probably, let's see. Let me kind of center this right there. It's probably not as fat as that. Okay. The dimensions are shown as 2 inches there. Feel free to grab a paper and just kind of follow through with this. So it's 2 inch, 4 inch, 2 inch. Okay. And I'm going to kind of draw this in 3D to kind of give you an idea. And essentially you would get so looking a little messy, but I think you get that idea. So remember, in strength of materials, we're always talking about cross-section, right? So what we see typically would be this cross-section right here, right? And, it's always a good habit to kind of visualize it being extruded outwards, right? Extruded outwards. Whether it's this way or that way, it really doesn't matter. Okay. Now, they actually tell you that the V allowable is equal to 150 pounds per nail. Okay. So what does that really mean, right? Is that if you went to Home Depot and you went to go buy a nail, that nail would feel a shear stress being able to hold 150 pounds of shear. Okay? It's not in this direction, right? Remember, that's where you get a hammer, you like punch it in, but it's shearing of the nail. I want to maybe move that aside for your reference. Up there, maybe make it smaller. Right? It's the shearing of a nail. Okay. Now, we are being asked to solve the V based on the spacing and the shear capacity of the nail. Now, remember, shear allowable is what you're allowed, the maximum allowed shear load on that nail. That's what it means, okay? And so what they also tell you in this problem is that this nail is coming in that way and that way. And that the spacing is at 3 inch on center. And sometimes they may not draw this in 3 dimensions, so that's why I'm drawing in 3 dimensions, is that and this would be given to you, is that the nail spacing, so you're solving for V, is 3 inches. Okay, so I have a nail here, got a nail here, boom, got a nail there, boom. That's that face right there below. I don't know if you guys can see it that way, but essentially you'll see that the nail is being shifted, nailed in every 3 inch on center. 3 inch, 3 inch. Okay. All right. And so this is like continuously being nailed, right? And so we know that shear flow, the equation, Q is equal to VQ over I. Now shear stress has a T, but we're focused on shear flow, right? So that Q is being put, so what we have to do is find out how much stress is being felt at 3 inches on center also. So we have to consider the spacing, right? So let's go ahead and start calculating some of the things. Is that if we have this, we have that V, the allowable shear, is equal to QI over Q, right? And so in order to have that, we know that Q is actually equal to 150 pounds divided by 3, which is to account for the 3 inch spacing, right? We have 150, it's 50 pounds per inch. So let's try to understand that concept, right? I don't want to draw on that messy thing anymore, is that if we have our nail spacing coming down, and those are at 3 inches on center, and we have another one, the shear flow, right? Let's maybe draw it like this. It's the shear that is flowing, it's at 50 pounds per inch. Okay, well, this thing is shearing at 50 pounds per inch. So the nail, this one nail, for example, has a 3 inch spacing, right? So maybe we take this middle one. So we say that half of this and half of this, that same distance, is 3 inch, right? So 3 inches is tributary to that one nail, right? So we know that the total shear is 50 pounds per inch times 3 inch, right? And so we get that it's equal to 150 pounds of shear capacity in the nail, okay? Hopefully that kind of makes more sense. And so let's go ahead, and this is really not important information. It's just for you to understand. Okay. So we've got that. So let's do kind of a check, right? Okay. We're solving for V. We've got Q. We don't have our I, but we'll get that. We have the uppercase Q. So, all we do is we kind of fill in the blank. So how do we find moment inertia? Well, that's easy. I 12 BH cubed minus BH cubed, right? So for those of us that don't know the shortcut, it's really cool. So I'm going to actually draw it out, is that if we have the shortcut only works if it's symmetric about both axes, okay? Let me kind of center this, sorry. And what it's saying is that let's take the big rectangle here, okay, which is then equal to 1/12 B 6 H is 2, 6, 8 is 8 inches. So base 6, 8 to the third minus what you're subtracting is this and this. So what that is what I missed out on dimension is that's 2 inches. So if we know that the total is 6 and this is 2 inches, we know, and hold on, let's see, this is 2 inches here. We know that if we were to combine those two rectangles into one, and we could do that because we're on the same axes, we're not moving away the axis, because remember it's bending about the x-axis, right? Then what we have is the base would be 6 minus 2, which is 4, so 4, and the height would be 8 minus 2, so 6, 4. 4 to the third power, right? And that would equal to 234.6 inch to the fourth. That's your inertia. Okay, great. So we got the I. Now we're solving for Q. So Q is first moment, or the moment area, right? So it's what we did for like centroid back in the days, if you can remember back to statics. But the process is really simple, is that what you have to do is just find Q. Again, drawing your beam. Okay. What we do is we find, it's just area times y bar, right? It's the area of the block that you're connecting to, right? You always start from this side going inwards as your correlated distance. And we could have also done it this way. It's the same thing because it's symmetric, right? Okay. So what we're doing is we're saying, well, how do we connect? How do we connect this element to this element, right? So the area of this, and then the y bar. Now the y bar is always the center of the member that you're looking at, which, right, that's, if you assume that that's all equal, that's the center. And the center over here, which is the center of the entire member, okay? What is that distance? That's your y bar. So what is the area? Well, the area is, I think we're saying this is 6 inches. And we're saying that that is 2 inches. So the area is going to be 6 times 2, which is 12. And we know that the distance of here to here is that this is, say, 2 inches. So we know that this is 1 inch right here. And half of that, so we know that this to here is 4 inches. Half of that is 2 inches. So 1 plus 2 is 3. So y bar is equal to 3 inches. So 36 inch. And the units would obviously come out to be 36 to the third power. And so what we're getting is very close to the answer at this point, right? So we check back up to our equation. Let's bring it down. Is that V is equal to Q I over Q. So do we have everything now? Yes, we do. We know that this is equal to 50. We know that the inertia is equal to 234.6 over, and the Q, which we just solved for, was 36 inches. And that gives you 325.83 inches, pounds. What's really cool about this is that just for this problem, what we'll do is we'll go 326 and round up. Why? Because my birthday is March 26th. So just letting you know, it's my birthday. I meant to have this problem as my birthday. So let's kind of go back and kind of talk and start about what we just did, right? Here in this problem, we were asked to solve for the allowable load, or the question would be, what load would cause my nail to have 150 pounds of shear load, right? So we know that the nail capacity is 150 pounds per nail. So if you were to go to Home Depot again and you bought a nail, it would have I'm not saying all of it, you'd find the nail that have the 150 pound capacity. That's the nail that you're using. Then you got to know what the spacing is, because the spacing relates to the shear flow. Here's our nail. There's a constant flow of shear going, and tributary to that nail is 3 inches, right? Total 3 inches. And honestly, it doesn't really matter. Maybe this was confusing, but it honestly does not matter if you say, hey, here's my nail, here's my nail, here's my nail, here's my nail, and they're all at 3 inches on center. Therefore, we take 50 pounds per inch of shear, multiplied by 3 is 150 pounds. The concept is the same because you have the same spacing. But this is the more correct way of looking at it, okay? Either way is correct, right? We're just trying to solve a problem here. I'm not trying to teach the next course. Okay, so from there what we have is we know that it's shear flow, not shear stress, right? Remember, shear flow is the stress is flow, right? And then what we do, we know that Q is equal to VQ over I. Then we say that it's VQ, or Q, lowercase q, I over uppercase Q. We know lowercase q because we were given that for the most part. We know how to take moment of inertia. Remember, that was statics review, right? So, and then Q, which is a first, it's just really your area times your distance. You did that in statics. So in summary, it's statics, and strength of material. That's the only thing that you really learned for the strength of material portion of this thing. All right. If you have any questions, please feel free to comment. All right. Thanks a lot.